All right, so we're in section 13.8. And we're going to talk about the extrema of functions of two variables. So we've done a lot of stuff with kind of geometry of these different surfaces. Today we're going to talk about maximizing and minimizing them. So if you think back, one of the big results of calculus has to do with the extreme value function. Or the extreme value theorem. The extreme value theorem tells us that if we have a continuous function for a single variable, that we're guaranteed to have a maximum and a minimum value on a closed interval. For functions of two variables, we have something that's very similar. So we have a continuous function of two variables. The function is going to have a minimum value and a maximum value at least one point in a closed bounded region. So rather than on an interval, we're talking about a closed bounded region. Closed means the region contains its boundary points, and bounded means it's a subset of a closed disk. So we're talking about some finite region, and the region contains its boundary. So we're doing kind of the three-dimensional analog to the extreme value theorem. The extreme value theorem is really, I was reading something this weekend, and they talked about the extreme value theorem being one of the four kind of pillars of calculus, the extreme value theorem. And it really has to do with it's kind of connected really deeply to the structure of the real numbers, the extreme value theorem. So it's a really important idea. So let's define maximum and minima just so we have a technical definition. The idea is intuitive, but we're just going to come up with a formal definition. So we're going to say that our function f of xy has a local maximum at some point if f of xy is less than or equal to f of ab, for all points xy in some open disk about the point. The local maximum, we're just talking about the behavior compared to nearby points. That's what our definition is telling us. We're comparing our function to nearby points. If the function nearby is less than the function at this particular point AB, then we have a local maximum. And we just turn things around for a local minimum. So f of xy has a local minimum at our point. We just turn our inequality around. So this is just saying that the function is larger everywhere else nearby compared to the function at this particular point. So local maximum and minima tells us how the function behaves compared to nearby points, is really how I think about it. And we're going to define critical points for a function of two variables in a way that's very similar to what we did for a function of a single variable. So everybody good with our definition? Our definition is just stating explicitly how we intuitively think about a local maximum or minimum. So our critical point, we're going to define a critical point. We're going to say f of xy as a critical point at some point AB. If, and we've talked about this a little before, the partial with respect to x at that particular point equals the partial with respect to y at that particular point, and they both equal 0. Or if one or the other of the partials, or both, don't exist. So really the only difference with our definition of a critical point is that we have both the first partials equal to 0. For a function of single variable, we just have one derivative to worry about. With function two variables, we have two first partials to worry about. So our critical points are when both of those partials are equal to 0, or one or the other, or both don't exist. We can show, we're not going to go through it, but we can show that relative extrema occur only at critical points. So this is our important theorem for this section. That to find a relative extrema, we're looking for the critical points of our function. And we've also talked about this idea if the first partial with respect to y and the first with respect to x and the first partial with respect to y are both 0, so both of our first partials then our gradient at that point is 0. So every directional derivative is 0 at that point. And if every directional derivative is 0, that tells us that our tangent plane is horizontal. We talked about that a little bit. So at extrema, our tangent plane is horizontal. So just like with a function of single variable at a maximum or minimum, our tangent line is horizontal. Function of two variables, our tangent plane is horizontal at a maximum or a minimum. We've gone over this idea a little bit as we worked through problems with tangent planes. So any questions on our ideas? So the ideas with local maximum and minimum, we're looking for critical points, and And those are going to be where our maxima or minima can occur. So let's look at a couple of examples, and then we'll extend this idea a little bit because sometimes things are a little more complicated. So let's say we have g of xy equals 9 minus x minus 3 squared minus y plus 2 squared. So first off, just thinking about this surface, if we say z equals 9 minus x minus 3 squared minus y plus 2 squared, what kind of surface is that going to be? So our level curves, will they be circles or ellipses? Circles. Our level curves will be circles, and this minus 3 and this plus 2 just shifts the centers, right? And then in the coordinate plane, so if we say y equals 0, we get z equals 9 minus x minus 3 squared. What kind of curve is that? Z equals x squared. We're going to get a parabola. And if we look at if we let x equal 0, we get z equals 9 minus y plus 2 squared. So some variation of z equals y squared. Parabola. So it's a paraboloid. And because we have this 9 minus, which direction does it open? Downward, right? So the problem here is to find any extrema. So we went through that little exercise because sometimes if we think about the problem, we don't even have to take any partial derivatives. So if this is a paraboloid that's facing downwards, where is it's going to be, the maximum is going to be at the vertex, right? And it's not going to have a local minimum because it just keeps opening downward. So where is going to be the vertex? So x equals 3, y equals negative 2, and then I could find the extreme value by plugging 3 and negative 2, and what would be what would z equal? Z equals 9. So that's our one maximum, is at the vertex. So for this particular function, because we had an idea of what it looked like, we could find the extrema just by, like your book encouraged you to do a lot last year, by being clever. And we could verify that by taking partial derivatives and setting them equal to 0. And we would get the same answer. And let me show you, so a picture, I have pictures of this one. So there's our picture of our nice paraboloid. So we have it opening downwards. There's our maximum here. Whoops. It's going up to 10, so it's just below 10, and we look at it from above. We see that we're at, are we 3, negative 2. So there's what our shape, a graph of our shape looks like. All right. So things can get more complicated though. Just like a function of single variable, a critical point doesn't necessarily give us an extrema, right? What else can happen at a critical point for a function of a single variable? You could have an inflection point. So if we don't necessarily get an extrema, we get an inflection point. For multivariable functions, we have, rather than an inflection point, and we've talked about them a little bit, we have saddle points. So a saddle point would be a function, we would add a point on a surface like this. So this is a hyperbolic paraboloid. So here, right in the middle here, it's a minimum if we're going this way, but if we turn it around this way, That point is a maximum. So it's a maximum looking from one direction, and it's a minimum looking for another direction. So that's what we call a saddle point. So we need to have some way to figure out if we have a saddle point on this surface. So what would you guess we would do to figure out if we have a saddle point? What do we do for a function of single variable? Second derivative. We had the second derivative test, right? And that would tell us if we had an inflection point. Well, we have something similar to the second derivative test. We call it the second partials test. So to test for saddle points, to test, and the second partials test will tell us, do we have a maximum, do we have a minimum, or do we have a saddle point? Just like the second derivative test, we can tell if it's concave down, we have a maximum, concave up, we have a minimum, so all those similar conditions. So we have the second partials test. And because we have several second partial derivatives, it's a little more complicated than the second derivative test. So we're going to say for our second partials test that f of xy has continuous second partial. So we're talking about a well-behaved function. Second partials in some open disk about our point. So we just need our function to be well behaved nearby where we're looking, and we have a critical point. So f, the partial with respect to x at our point, equals the partial with respect to y, and they both equal 0. We're going to define this quantity. Let d equal f sub x, the second partial with respect to x, times the second partial with respect to y, minus the mixed partial and we can call a lot of books call this, it's kind of like our quantity in the quadratic formula, the part that's under the square root. We call it the discriminant. So we call this the discriminant. So we have.
Is that a real D or a commercial D?
That's just the letter D. So this is just the letter D. So D, the discriminant is this quantity. We have several conditions depending on what is happening with D. We have 4 conditions. 1, if D is greater than 0, and f sub xx is greater than 0, then f has a relative minimum. At our particular point. Our second condition, if D is greater than 0, and our second partial with respect to x is less than 0, then f has a relative maximum. at our point. Our third condition, if d is less than 0, then we have a saddle point. So our point AB, f of AB, is a saddle point. And our last condition is if d equals 0, we can draw no conclusion. So those are our 4 conditions with our second partials test. So for our second partials test, we calculate this quantity and we compare them to these conditions. And the conditions here are very similar to thinking about concave up and concave down, but because we have partials going in the x direction and the y direction, we have to take kind of the behavior of the function in each direction into account. So this is our second partials test, which is kind of the analog to the second derivative test. So any questions on that? All right, so the last thing I want to do is just work out a couple of examples finding relative extrema. So let's look at f of xy equals minus x squared minus 5y squared plus 10x minus 30y minus 62. So there's our function, and we want to find the relative extrema. So just looking at this function off the top of trying to figure out what it looks like, it's not set up really nicely to figure out what a graph might look like. So it's a little hard to do this the way we talked about the paraboloid. So we're going to go through our process. So the partial, what's our partial with respect to x of this function? Minus 2x plus 10. And the partial with respect to y? Minus 30. So where are our critical points? X equals 5 and y equals negative 3. So those points are going to be where the partial of f and the partial with respect to x and the partial with respect to y are both 0 at the same time. Second partial with respect to x for our second partials test. F sub xx is negative 2. F sub yy negative 10, and f sub xy 0. Partial of f with respect to y is just going to be 0. So our discriminant d equals negative 2 times negative 10 minus 0 squared, and that is 10. So d is greater than 0. What's that? Oh, 20, yes. Thank you. So d is still greater than 0. D is greater than 0, and f sub xx is less than 0. So we look at our list of the conditions, and we say that f of 5 negative 3 is a relative minimum? Maximum, yes, I'm sorry. So our function, we're going to have a maximum at that point. So let's look at what this surface looks like and just compare our results to the graph. So here is a graph of that particular function. So we get this kind of curve here, and then if we look here from the top, we get a maximum right up here on the top of this oval. And here we are at 5, is it -2 or -3? -3. So our maximum is going to be right up here on the top of this little piece here. So finding relative maximum minimum, not necessarily difficult. There can be a fair amount of work to do, depending on the function, depending on how you have to go about finding where the first partials are 0 at the same time. But the process is not particularly complicated. So let's look at one more example that's a little more involved. So we have our function is 2xy minus 1/2 x to the 4th plus y to the 4th plus 1. So looking at this function written out this way, I would have no idea what the graph looks like. And we want to find the extremum, relative extremum. So let's go through our steps. We're going to find our critical points first. So the partial with respect to x, what's partial with respect to x here? 2x. 2y plus minus 2x cubed. There we go. So there's our partial with respect to x. What is our first partial with respect to y? 2x minus 2y cubed. So it's symmetrical in x and y, right? So how are we going to find our critical points here? Solve for 0. So first off, just by looking at these, 1 1 is going to work, and what else is going to work? 0 0, and so we know just by looking at these by inspection we can see that 0 0 is going to be a critical point. 1 1 is going to be a critical point. -1 -1. So we have these 3 critical points. Would we have any more?
No.
Eric says no. Why do you think that?
Well, because you have the cubed.
The cubed? It is, so we have an exponent of 3 here and an exponent of 1 there. So we're going to guess that we would have three solutions, right? A maximum of 3 solutions. We could go through the algebra to find the maximum minimum. We could solve one of these equations for x or y, plug it into the other one, go through that. But this one's pretty easy. We can look at it and see by inspection. So now we have our critical points. So these are our critical points. And we need to run our second partials test. So we need some second partials. F sub xx. What's our second partial with respect to x? minus 6x squared. Second partial with respect to y, f sub y, y. Minus 6y squared, it's symmetrical in x and y. And then our mixed partial, f sub xy, 2.
Do you have to find f to the xy, or can you do it between even y?
If our function is continuous, then the mixed partials are equal. Right, so they would be the same. So now we need to find our discriminant at each of these 3 points to decide if each one is a maximum, a minimum, or a saddle point. So we're going to run at, let's do the 1, 1 first. So our discriminant at 1, 1 is going to be minus 6 times minus 6 minus 2 squared, which is going to be greater than 0. So at 1, 1, our second partial with respect to x is less than 0, and d is greater than 0. So we have a relative max. And at -1, -1, we're going to come up with the same thing. So d of -1, -1, we end up with a relative max as well. So we get 6 -6 minus 2 squared again. So -1, -1 is a relative max. And then we're going to run our discriminants at 0. D of 0, 0. We get 0 minus 2 squared, which is less than 0. So 0, 0 is going to give us a saddle point. So we have 2 relative maximums and a saddle point. Let's take a look at what this function looks like, what the graph of this function looks like. So here's our surface. Here's our saddle point. If we look at from the side, we can see it dips down just a little bit here. So our saddle point here at 0, 0. And then our maximum at -1, -1, and 1, 1 here. So we get a saddle point here and a maximum on either side of it. So any questions on our critical points and our second partials test? All right, so things start getting more interesting when we talk about absolute maxima and minima, because for an absolute maximum and minima, we're looking at a function and we're bounding it. We're talking about a boundary. So not only do we have to examine the relative maximum and minima on the interior, we have to examine the boundary, just like we do for a function of a single variable, and examining the boundary can be difficult. Not difficult, just algebraically can be kind of messy. So our homework, page 958. There you go. You will get then